solubility. What did you have to do when you made your potassium tartarate solution? Your KHT lab with the titration. It's in units of grams per milliliter or moles per liter, right? So it's in unit of some sort of concentration, right? What does that concentration represent? All right, what was the first step when you made the KHT solution? And the reason I'm just bringing it back to the lab is something you physically did that's related to these theoretical concepts that we're talking about here. Oops, forgot to hit record. How much potassium tartarate did you have to dissolve in solution? Did you dissolve a lot or a little bit?
A lot.
A lot, right? So you did a lot and then you had to filter out the rest. So what kind of solution did you create? A saturated solution. That was the whole point of that, right? Is the maximum amount in grams per liter or moles per liter you can dissolve, right? That's what our molar solubility was defined as, right? The maximum amount that we could dissolve. And so how do we relate this to equilibrium? Well, in terms of the solubility product, that was the concentration at equilibrium of whatever ion it is that you're dissolving in solution, right? So if we had something like calcium carbonate, CO3, and we were dissolving this, it would go to calcium 2 plus carbonate 2 minus. These are in the aqueous phase because now they're dissolved, right? With the whole idea with the solubility product is now we're just looking at this process of breaking the ionic bond between these ions and then solubilizing them in water, right? We're just using ideas of equilibrium applied to this. So the solubility product, right, the equilibrium constant for this type of process, which was called the solubility product, is just equal to what for this specific reaction?
It's just equal to CO3.
Yep, Ca 2 plus, CO3 2 minus, right? Just the concentrations of those. In how we related the molar solubility, right, which was the maximum amount that we could dissolve in solution, it's equal to these concentrations, right? This concentration is equal to the molar solubility, the equilibrium concentration. Why? Because, well, once we've put the solid in the solution, we have some initial mixture, right, that isn't at equilibrium. It always trends to move towards what? What does everything in the universe tend to move towards? What state? We've only talked about equilibrium, right? So it's not going to move towards a non-equilibrium state. It's going to move towards equilibrium, right? So that equilibrium concentration is going to be the maximum that's allowed to be dissolved at that equilibrium. All right, so that was equal to the molar solubility. The specific concentration of that ion, and in this case, we would say that both of these, the KSP and the molar solubility would follow the same trend. We could compare it because the stoichiometry is 1-to-1 in this case. So that concentration itself is equal to the molar solubility. I know we call them different things, but the maximum amount that you can dissolve is just the equilibrium concentration when you put that solid in the liquid, is kind of the idea. So we talked about molar solubility, and I forgot to mention, but before that we also talked about the French guy's principle, Le Chatelier's principle. And what was Le Chatelier's principle? What did that state? The general form of Le Chatelier's principle.
Changing the concentration, temperature, pressure of equilibrium will state a new rule of equilibrium.
Yeah, basically once you stress the system will respond to reduce that stress, right? So the basic idea is that stressing an equilibrium system will cause the system to respond to reduce that stress, right? And there was a couple different ways we talked about, right? So I know I mentioned all of them. We could have the concentration change, we can change the pressure, and I'm just gonna put delta to represent change in pressure, or we could change the temperature. Those are the three different ways that we kind of discussed, right? Change in concentration was relatively straightforward. If we add something to a chemical equilibrium, the reaction will just shift to reduce the concentration of whatever it is that we're adding, right? If we remove something, the concentration will just shift, or the reaction will shift to just add concentration to whatever it is that we're removing from the system, right? We're just moving in the direction that opposes that change. Pressure was a little bit different, because we had to have what kind of reactants in products or products? We had to have gaseous reactants or products, right? And this was increasing the pressure is like decreasing the volume. Remember, this is the one where we're kind of going in a chain of thought on what's actually happening. When we decrease the volume for gases, we're effectively increasing the side of the reaction that has more moles of gas, the concentration of those species, more than the other side of the reaction that has less moles of gas. So let me just write these, right? So change in concentration, we increase reactant or product, we then shift to decrease that reactant or product. Right, so if we have A plus B goes to C plus D, and we increase A, the reaction will shift to the right. If we increase D, the reaction will shift to the left, right? Because we're opposing that change. If we decrease the reactant or product, then we shift in the opposite direction. Right, so if we decrease A, the reaction will shift to make more of A. If we decrease D, the reaction will shift to make more of D. For a change in pressure, right, this depended on the number of moles of gas on reactants / product side, and what was the condition that had to be met where a change in pressure would shift the equilibrium. Right, there was something about the moles of gas in products and reactants that had to be true for the pressure to actually change the equilibrium.
I know it has something to do with volume because it increases.
It does, right? As we change the pressure, the effective way we're doing that is by increasing or decreasing the volume. When we do that, we effectively change the concentration of the reactants or the products. Right, so it did have to do something. What else do we have in, if we're doing this at constant temperature, we have P over RT is equal to N over V, right? That was our ideal gas law. That's basically why we can do equilibrium in terms of pressures, right? It's because the ideal of real gas laws. So so when we change the volume, that will effectively change the concentrations. But what condition has to be true for that to happen? Specifically in relation to the moles of gas for reactants and products. What do you guys think? So if we have the same number of moles of gas on both the product and the reaction side, and we change the volume, right, the effective concentration of just reactants and products stays the same, right? The ratio stays the same because we're changing the concentration the same on the reactant side as on the product side.
Yeah, it's the stoichiometry.
It had to do with the stoichiometry, right? And specifically what it was, we had to have a different number of moles of gas on one side of the reaction compared to the other, right? That can be 1 and 0, it can be 2 and 1, it can be anything that's just not equal to each other, right? So the condition for this that had to be met was that delta N, which is equal to the sum of the moles of products of gas minus the sum, right, I'm just writing it out in math terms, of the reactants of gas has to equal 0, or not 0, has to not equal 0. Right, so this couldn't be equal to anything non-zero, right? We can't have the same number of moles of gas on the products and the reactant side. And the reason for that is because as you change the volume of the entire system, which is both reactants and products, if you have more moles of products, for example, right, and you're reducing the volume, you're increasing the concentration of those more than you're increasing the concentration of the reactants. Why? Because there's just more moles of gas, and the concentration is just related to more moles of gas. So we can actually change the volume, whereas liquids and solids are not compressible, so when we change the pressure, it doesn't change the volume very much. That's why pressure affects the equilibrium of the system. Right, so this is the main reason why, or the main condition for allowing pressure to change the equilibrium of the system. And so, if we have here, we'll use this example, 2A gas goes to 3B, which is also a gas. Right? If we increase the pressure, we're effectively decreasing the volume, right, for the entire system, both reactants and products, but we're doing it at a ratio of 3 to 2 in favor of the products, right? We're increasing the concentration more for the products in this case than the reactants. Why? Because as we decrease the volume, the concentration goes like 3, which is the number of moles of B, whereas for the reactants, it only goes as 2, right? As a factor of 2, because we only need 2 moles of A for every 3 moles of B. So this is going to, right, this is going to decrease the volume, which increases the concentration, right, for everything in the system. It's not just increasing the concentration of the products, it's increasing the concentration of the reactants and the products, right? So we increase the pressure, right? The pressure is proportional to to 1 over the volume. So that means we're decreasing the volume, and the concentration is equal to N over V. Right, so as we decrease the volume, the concentration goes up. The concentration of all the reactants and the products is going up in this case, but the products, it's going up more because there's more moles of gas on the product side, right? It's increasing more because there's more moles of gas. So then the reaction should shift the same way it does for concentration, away from the moles, the side with more moles of gas. So this will shift left. Right, it's going to shift away from more moles of gas. Why? Because the concentration of more moles of gas is changing more than the concentration of less moles of gas. If we were to decrease the pressure, then we're increasing the volume, which means that we're decreasing concentration, right? And so with the same idea, we're decreasing the concentration of the side with more moles of gas more, so the reaction is going to shift to make whichever side is reducing its concentration more. Right, so this is now going to shift right, because we're effectively decreasing the concentration of B more in this case than we are A. Alright, so this is, out of all of them, this is kind of the one where you, okay, I gotta sit and think for a second, how does pressure changing the reaction? You can just remember that more moles of gas, if we increase the pressure, you're gonna shift away from it. More moles of gas, if you're decreasing pressure, you're gonna shift towards it. All right, because it depends on each individual reaction. If we have, more reactants, then these arrows would go the opposite way. Any questions on that? Just because I know this is kind of the one that takes a little bit to wrap our heads around. Okay, and then the last thing that we talked about was a change in temperature, right? And what did this depend on? What did a change in temperature? How do we treat that in terms of equilibrium? How do we know which direction the reaction will shift?
Oh, wasn't it? It was endothermic.
Yeah, it depends on the energetics of the reaction. Right? If it's endothermic or exothermic, and if it was endothermic, right? What was the way that we could treat the energy in this reaction, right? We can when we think of temperature, right?
Reactant.
Yeah, we treat the heat or the temperature as a reactant, right? We can treat it, temperature or heat is treated as a reactant, right? And so if we treat it like a reactant, we just treat it the exact same way we treat any other reactant. So if we increase the heat, right, for an endothermic reaction, which direction should the reaction shift? It should shift to the right, right? The same way that if we increased the concentration of A, it shifts to the right. If we increase the concentration of the heat, right, which is a funny thing to say, but that's how we can, think of it. If we increase concentration of the heat, we'll respond by shifting the opposite way. If we decrease the concentration of the heat, which way will we shift? The opposite way, right? So we're gonna shift to then make more heat, right? And the way we think of this, physically what's happening is the system is going to respond in any way that reduces or counteracts the change that's being applied to the system, right? So if we lower the temperature, that means the system wants to respond by increasing the temperature. How does that happen in an endothermic reaction? Well, that means the reverse reaction happens, right? Because if we just flip an endothermic reaction around, it's an exothermic reaction, this direction will release energy as the reaction proceeds. If we increase the temperature of the system, the reaction will move in a way that reduces the temperature of the system. So an endothermic reaction going in the forward direction takes in energy from the surroundings, right? So it takes in heat from the surroundings to then reduce the temperature. So it's going to move in the forward direction like that. So there's a physical interpretation, and there's also the device we have. We just treat heat as a product or a reactant. If it's exothermic, how do we treat the heat? We just treat it as a product. So it would be A plus B goes to C plus D plus the heat, right? And then it's the exact same idea here. Now if we increase the heat, we shift to the left. If we decrease the heat, we shift to the right. And we see the exact same physical principles as this one, right? For an exothermic reaction in the forward direction, it releases energy, so it releases temperature, or increases the temperature as the reaction goes in the forward direction. If we increase the temperature of the system, right, the reaction goes in the reverse direction to lower the temperature, right? Because the reverse reaction for an exothermic reaction is an endothermic reaction. All right, so Le Chatelier's principle, very important for just kind of understanding, if you're ever working in the lab and you want to change the concentration of something, or you want to increase the solubility of something, you can just use these simple principles to actually do a lot for your system. And the qualitative analysis labs that you guys are actually doing in lab today deals a lot with these kind of different effects, how they change solubility of certain things, how they increase or decrease the solubility, right? So if we increase the concentration of an aqueous ion, it can go back into the solid phase and things like that. All right, any questions on what we talked about last time? So I know it was a lot of information, but. No, okay, all right, so we're gonna continue with solubility part 2. And so where we're gonna start off with is last time we talked about molar solubility, and then using that to determine the solubility product for a dissolving or dissolution process. And so we can also ask, how does the solubility depend on the existence of a common ion, right? So a common ion, right? And all that means is that, let's say we have a solution with sodium chloride in it, and we're trying to dissolve let's say lead 2 chloride, which is a solid, right? How does the presence of salt in our solution affect the solubility of lead chloride here? And so this is actually why we use distilled water, or you should be using distilled water in the qualitative analysis lab, right? Because if you have a common ion and we're looking at the dissolution, so maybe a reaction like this, Pb2 plus aqueous plus Cl, or 2Cl minus aqueous. If this is our dissolving reaction and we have a bunch of sodium chloride in the solution, then that'll affect how much of this we can actually dissolve in the solution, right? It'll affect how much of this forward reaction happens. This is the same thing with an ice table. If we already have some product and reactant in a gaseous mixture, right, we have to think about how that change affects both the products and the reactant side of a chemical system like this. Then I accidentally made an extra slide, but I'll delete it in a second. Give you guys a second. And so does anyone have any idea how this might affect it?
increase the amount of reactant, or, yeah, reactants.
Yeah, right, if we have a bunch of this present already in solution, right, if we add a bunch of this to the solution, which way is the reaction gonna move? Right, from Le Chatelier's principle, you can point left or right. Right, if we add a bunch of chlorine ions to solution, which way will the reaction move? Left or right? It should move left, right, because we're increasing the concentration of this, right? Which means the reaction will shift to the reactant side, which is the solid, right? So that should crash something out of solution. Right, and so Le Chatelier's principle says base in the presence of, so here we have a different example, we have calcium fluoride, cause the equilibrium to shift to the right to decrease solubility, right? So if we increase the amount of fluorine or fluoride ions in solution, the reaction will shift to the left. And in this case, that causes less solid to be dissolved in solution. And so, in general, the solubility of an ionic compound is lower than a solution containing a common ion. The only times it's really not lower is when we have something like coordination compounds or complex ion formation. Right, does that make sense to everyone why increasing, right? We know if we are at equilibrium, we add a bunch of fluorine to this solution or fluoride ions. We know that Le Chatelier's principle says that that's going to shift it opposite, right? To use up a lot of those fluoride ions, so we're not, so we're opposing the change that we're stressing the system with, right? So that's why it shifts to the left. But in the context of solubility, what that's saying here is that, well, if we have that already in solution, we add a bunch of solid, less of that solid should dissolve into the aqueous phase, right? Because the equilibrium, to keep whatever this ratio is, right, the equilibrium constant the same, because we already have a bunch of this, that means we're going to have to shift the reaction to the left there. And how do we interpret that? Well, that means that it's going to be less soluble in that solution because there's already some other ion that's kind of taking the spot of the maximum amount of concentration we can have of this in the solution. All right, so let's say we have a solution of barium sulfate, and we want to ask which solution is going to be most soluble in. So why don't you guys take a second and think about, out of these three, which one should it be most soluble in? And start off, get some practice writing the dissolution reaction, right, or the dissolving process. What's the dissolving process actually look like here? Or the reaction that represents that dissolving process? So what's the dissolution reaction for barium sulfate?
C.
C will be the right answer, so that's correct. But what's the dissolution for barium sulfate?
Oh, BA plus.
Right, so it'd be SO4, solid, right? Barium sulfate is our solid. We put it in water, and we get Ba2 plus aqueous plus SO4 2 minus aqueous, right? So if we're determining which one is going to be the most soluble, what ions are we going to be looking at? The concentration of what ions is going to affect the solubility of this compound. Right? The existence of what ions already in solution will affect the solubility of barium sulfate.
Barium or sulfate.
Yeah, barium or sulfate, right? So one of these two ions, right? The presence of either of these should shift the reaction in which direction? Right or left? All right, if we add sulfate or barium ions to solution, which will it shift? Left or right? Left, right? Because we're adding concentration of products here, right? Should shift the reaction left. And so this compound, sodium nitrate, is the only compound here that doesn't have barium or sulfate, right? So here we have sulfate ions, here we have barium ions. So that's how we know that this is going to be the most soluble in sodium nitrate. And we can understand that because this dissolution reaction, NO3, 2, is going to be barium 2 plus, NO3, 2, aqueous, 1 minus. Let me write this a little neater. What the hell? Right, so where am I getting the charges? How do I know the charges for these ions when they dissolve? How do I know that barium is 2 plus? Like, let's say you didn't remember your polyatomic ion charges and names, right? How would I know that I'm still gonna have a 2 plus barium there? And so for the solubility rules and for probably a little bit of, once we get into electrochemistry and stuff, probably sometime in November, it'll be kind of important. So remind ourselves right now, if you're in group 1, what's your preferred oxidation state? And when I say preferred oxidation state, I just mean charge, right? So it should be +1, right? Why? Because it's easy for you to lose 1 electron and get a noble gas configuration. It's easier for you to lose 1 electron than to gain 7 electrons. Barium is in what group? Group 2, right? So that's why barium has a +2 charge. So let's say you didn't remember that sulfate is 2 minus. I didn't remember that. I just knew barium is 2 plus. And that this compound should be electrically what? For an ionic compound, what should the total charge on that compound be? 0, right? It isn't until we get complex ions that we can have more than, or non-zero charge, right? So I know the total charge has to equal 0. So that's how I know sulfate is 2 minus there. What about Na2SO4? Don't need to put parentheses around that. Sodium sulfate will have 2 sodium ions. They're each +1 because it's in group 1, and sulfate 2 minus. Right, so that's where I'm getting these charges from. Now I remember what this is just because I know this has to be neutral. Here's sodium. If I remember group 1 needed to be +1, I know this is -2. For this to be neutral, I need 2 times whatever that charge is, and it has to be positive, so it'll be 2 times +1. And then both of these I forgot to put, but both of those are solids, right? These are all solids, and we're dissolving them or they're already going to be dissolved in solution, right? So these are already in solution, and that's how it's affecting the solubility of the solid that we're looking at. Okay, and then the last one, we have sodium nitrate, solid, goes to Na plus, aqueous plus, NO3 minus aqueous. Both of those are going to be positive and minus 1. All right, and just to review, with chemical reactions as well as with ionic compounds, we have to have conservation of charge on both sides of the reaction, right? We have to have the same net charge on this side as we do on this side. Because this is neutral, that means that this has to be neutral. If this was -1, then this side would have to be -1 as well. So just things to keep in mind as we're kind of going over stuff, right? But the only one that affects the solubility, or that won't affect the solubility of barium sulfate, or won't affect it much, will be the sodium nitrate here, right? Because of the common ion, there is no common ion in sodium nitrate, so it shouldn't affect the solubility of the compound that we're looking at. How do we know that? We write the dissolution equation for this dissolving process, and we just try and identify what ions are present in these other compounds. And then we analyze it using Le Chatelier's principle. Which way does that force the reaction to go? If it forced the reaction to go this way, then that would increase the solubility. If it goes that way, then it decreases the solubility. All right. Okay, any questions on that one? All right, so here we have another example, except this one, we have a more explicit question being asked. How is the molar solubility of calcium fluoride in a solution containing 1 molar sodium fluoride compared to that of pure water, right? So you're gonna look at what is the solubility, right? And what kind of solubility? The molar solubility, right? What is the molar solubility defined as? Then I just have to give you a value while you guys think about that. I forgot to put the KSP. KSP for this reaction is equal to 1.46 times 10 to the minus 10. Let me write that a little neater. To the minus 10. I didn't really write it in here. Right, what is the molar solubility?
Maximum you can dissolve.
The maximum you can dissolve in solution, right? And how is that related to KSP in these cases? Right, it was, what was it?
It's equal to Ca plus.
Yeah, it would be equal to
Or times,
this,
yeah.
this concentration of calcium here, right? Because when we solve for the equilibrium concentration here, we set up an ice table, we look for the change. Initially, we start off with 0 of this, and all the change is going to be related to some arbitrary change we call x. Once we solve for x, that tells us the molar solubility, right? Because x is how much of this we lose, right? That's how much of this gets dissolved into solution. So that's why solving for x in the ice table for these molar solubility and solubility product questions gives us the molar solubility, right? Because x represents how much of this we lose. And this was the maximum we can dissolve in solution. All right, and you're comparing 2 different cases here. You're comparing it sodium fluoride, and you're comparing it with pure water. You're comparing sodium fluoride, present sodium fluoride, and pure water. How do you think sodium fluoride will affect the equilibrium? Yeah, it should shift it to the left, and it shifts it to the left. Does that make it more or less soluble?
Less.
Less, right? Because it shifts it from aqueous, which means soluble, to solid, which is insoluble. So this is exactly what's happening when we're precipitating, right? So first we'll calculate it for pure water, right? If we set up an ice table, we have CaF2, Ca2 plus, 2F minus. We initially have, we have some amount, right, of calcium fluoride. We have 0 of each of our products before we dissolve it, right? We have 0 of these. We have some initial amount, but that doesn't affect the position of the equilibrium once we get to equilibrium concentration, right? Because it's a solid, it doesn't go in our equilibrium constant. What states that matter go in our equilibrium constant? Aqueous and gases, right? Those are the only two things that affect our equilibrium constant, right? So how much of calcium fluoride do we lose? Minus X, right? Because we're starting with all solid. And then how much calcium do we gain? Plus X. And then what about fluoride ions? Plus 2X, right? Because we have a coefficient 2 there. This coefficient 2 is why we have a 2 there, which means our equilibrium concentrations are going to be X and 2X. Our equilibrium constant, which is equal to our solubility product here, is equal to what? Yeah, we can put in a numerical value, 1.46 times 10 to the minus 10, which is equal to right, what do we plug into our equilibrium constants? We plug in concentrations, but specifically what concentrations do we plug in? Do we plug in initial concentrations into our equilibrium constants? We plug in the equilibrium concentrations, right? Which is what we had to use the ice table to solve for, right? Those are our equilibrium constants. That's the whole point of doing the ice table, is just to get values for the equilibrium constants here. And so this is equal to Ca2 plus F minus squared. I'm gonna put this on the next page, right? These are the equilibrium concentrations of these, which are what we just used. The ice table, oops, I did those in the wrong order. What we used the ice table to solve for. Okay, so then we get 1.46 times 10 to the minus 10 is equal to x times 2x squared, which is 4x to the third. So we get 1.46 times 10 to the minus 10, divide both sides by 4, divide both sides by 4, and then how do we get rid of the, not x squared, x cubed? How do we get rid of the cube here? Exponent of 1/3, right? We raise both sides to the power of 1/3. And then that gives us our answer. That gives us x because it's 1/3 times 3 equals just x. It's 1.46 times 10 to the minus 10. Divided by 4 to the 1/3. And so when we plug those values in, I feel like getting my calculator out, you should get 3.32 times 10 to the minus 4. Equals 3.32 times 10 to the minus 4. And this is going to be a concentration, so we'll just put molarity here, right? So that gives us the molar solubility. Why? Because at equilibrium, this is the amount that's going to be dissolved in solution, which is the maximum amount that we can have dissolved in solution. And it's equal to the amount of calcium fluoride that we actually dissolved, right? How do you know that? Well, in our ice table, right, it was minus x, right? We solve for x. X is what we're losing of the solid state that's going into the aqueous phase. Just leave this up to give you guys a second. And so if you're done with that first part of the question, see if you can figure out then what the presence of 1 molar sodium fluoride, how that will affect the solution. Or the molar solubility. And you notice in the problem, you can just set it up. I have something in parentheses that says the small x approximation. I'll introduce you guys to an approximation that you're going to be making a lot over the next month. And it has to do with x being small, which is why it's called the small x approximation. All right, so now see if you can set up what's the solubility in the presence of 0.1 molar NaF. Right, so what we just did was in pure water, right? How do you know? Well, there was no common ions, so you start off with 0 of each of your products. How is the presence of 1 molar? So what changes for our ice table by having sodium fluoride presence? Present, not presence.
Would there be another fluoride ion?
Right, when we add sodium fluoride to solution, sodium fluoride is a strong electrolyte, which means it dissociates completely, just like sodium chloride. So it completely dissociates into these 2 ions, right, because it's a strong electrolyte, which means that the concentration of sodium fluoride is equal to our concentration of what in solution? Strong electrolyte. So the concentration of NaF is equal to the concentration of what in solution? And so a strong electrolyte is similar to a strong acid or base. Does anyone remember what a strong acid or base does when it gets in solution? May have been a bit. A strong acid or base dissociates completely, right? Which means that if you have hydrochloric acid, you get 1-to-1 ratio of hydronium and chlorine ions in solution. So if we have a strong electrolyte, it's the same principle. We should get a 1-to-1 ratio of sodium fluoride to fluoride ions, right? So that should be the same concentration as our fluoride ions and our sodium ions, right? Do either of these in solution affect our solubility of what we're looking at? This one affects our solubility, right? It means that we already have some in solution. And so if we add fluoride ions to the solution, which direction should this reaction shift? Left, right? Which means that should we be increasing or decreasing the solubility? This should decrease the solubility, which means that the value that we calculate, right, we already have an idea, okay, this value should be less than the value that I just calculated, right? So I already start off with some of this in solution. And specifically, how much do I start off with? 0.1 molar, right? So our initial amount is 0.1 molar of our fluoride ions in solution, right? And we start off with an arbitrary amount of calcium fluoride, and we still have 0 calcium initially. It's the presence of this strong electrolyte that gives us fluoride ions that then moves the reaction, right? So you move it to make it less soluble. And what are our changes going to be? Are they going to be different from before or the same? How would they be different if they were gonna be different? Yep, now we started off with this, and let's say we didn't know which way the reaction was gonna go initially. How could we always determine which way the reaction should move? What can we compare to the equilibrium constant to determine if the reaction will go forward or reverse? The number of moles, you can do that if it's a gas, right?
Isn't there another equilibrium?
There was the reaction quotient, which was Q, right? And you can compare Q and K to each other, and that'll tell you which way the reaction will go, right? So if Q is less than K, then that means you have less reactants, or you have more reactants than you have at equilibrium, so the reaction will shift right. From this one, you know that the reaction will shift right just because our concentration of calcium is 0 initially, right? Which means our Q is going to be 0, right? Our QSP would be the initial concentrations, which would be F minus 2, right? If this is equal to 0, then QSP is equal to 0. And even though KSP, right? So how does 0 compare to, what was it, 1.46 times 10 to the minus 10, right? This is really, really, really small, but is it bigger or smaller than 0?
It's bigger.
It's still bigger than 0, right? So this is going to be QSP is less than KSP, which means that the reaction will shift to the right, right? And the direction of the reaction shift tells us what about our change? What information does that give us?
It's still gonna be like minus X.
It gives us the sign of the change, right? If we're shifting to the right, it would get plus or minus of calcium fluoride. We get minus again. And we get plus or minus of fluoride and calcium. Plus, right? So this will be minus, and this will be plus, plus again, right? So this means that the reaction will shift right, and that gives us the sign. And then how much of the calcium fluoride are we losing? It's an arbitrary amount, right? It's still the same as before, it's just X. And how much of the calcium are we adding? X. And then what about the fluoride ion? 2X. Right? It's still the exact same chain. Why? Because the reaction is still going in the same direction, whether you have sodium fluoride there or not. Right? We're still moving in the right direction. The only way this would change is if all of a sudden the reaction moved in the opposite direction. Well, how would you know if it did that? Well, if you had both of these ions present in solution. Because there's 0 here, you still have to shift to make some of the products here no matter what. How much are you going to shift? Well, a lot less than you did before because now you have already some of the fluoride ions present in solution. And so what are our equilibrium concentrations now? We have X, and then what is it for?
2X plus 0.1?
Yep, 0.1 plus 2X. Right, so these, again, the whole point of the ice table is just to get these equilibrium constants. Right, we just want, this is the only thing that's interesting here. We don't care about calcium fluoride. Why again? Why don't we care about equilibrium concentration of calcium fluoride? Because it's a solid, right? Solids aren't included in our equilibrium constant. So now we have, once again, KSP is equal to X times 0.1 plus 2X squared. And I say, okay, well, I don't know the general form of the solutions to a cubic equation anymore, right? So before we had a quadratic equation that has 2 solutions. Cubic equation will have 3 solutions. and we don't really have a way to solve for that easily, right? So what we do, or what we can do here, is we can do what's called the small x approximation. And we'll see this a lot more, especially when we get to acids and bases, but we'll see it, we can use it right now too. Is we have this small x approximation. And what it says is because KSP is much smaller than 1, so it's a very, very small value, this reaction is just going to shift a very, very tiny bit to the right. Right? We should still have mostly, because KSP is so, or calcium chloride is so insoluble, right? Its equilibrium constant is very small. It means we don't shift to the right very much. Well, how do you know that? Well, this is the ratio of the products over the reactants at equilibrium. We don't include the reactant, but since this is very small, it means our concentrations of calcium and fluoride are very small as well, right? So those concentrations, right, are related to this value x. It means as we shift in this direction, x is going to be very small because KSP is very small, right? So if we're adding two numbers together, 0.1 and 2 times x, which we know is very small, right? It's probably on the order of 10 to the minus 5 or something like that, right? This is basically like adding 0.1 and 0, right? We can just assume that this number doesn't change much by adding x to it, right? So because x is so much smaller, this implies x is much smaller than 1. So 0.1 plus 2x is approximately equal to 0.1. And if you wanted to, convince yourself, I used to have a professor that loved that as a homework question, convince yourself of this. Everyone would always go, what does that mean? He will say, well, just sit and convince yourself of it. So what do I turn in? Well, just convince yourself of it, and then you did it. So if you wanted to convince yourself, you could actually plug in some numerical solution for whatever cubic equation you would get here. And you would see, okay, well, this is like 10 to the minus 5, which is like 0.00001. And if you add 0.1 to that, it'll be like 0.99999, right? So that number is going to be very close to 0.1. And so how do we simplify things? Well, a lot of times in math and physics and chemistry, what we do, we say, okay, well, this simplifies the math a lot, so we're just going to ignore that part right there, right? So this allows us to, instead of solving a cubic equation, now we can set KSP equal to x times 0.1 squared. All right, so this is kind of nice when we're able to do this, right? And so this is also how we're going to treat reactions if you have higher powers of x2, right? What if we have power 6? Well, if I just get rid of the x there, now it's just 0.1 to the power 6. That's a lot easier to deal with than trying to factor 6 of these multiplied to each other. Right, so this is the new equation that we're going to use to solve for our equilibrium concentration. And so I'm going to put this on the next page. Once I give you guys a second to finish writing. But again, you don't have to remember the justification for this, right? You can say, well, if my equilibrium constant is very, very small, and I'm moving to the right in this case, that in general means that I can usually ignore a sum of this x value with something that's somewhat comparable, or somewhat comparable to a more macroscopic value, right? This is 10 to the minus 1, 10 to the minus 5. Those are really, really far away from each other. So I can assume that that is basically equal to 0 there. Right, so then we get 1.46 times 10 to the minus 10 divided by 0.1 squared is equal to x. And so when you do that, this is like 10 to the minus 2, 10 to the minus 10, 1.46. Right, we can do this without having to put it in our calculator, we get 1.46 times 10 to the minus 10 minus 2, which gives us 1.46 times 10 to the minus 8 is equal to x, right? And this is our solubility, right? Still represents the solubility of our calcium fluoride. So is this less soluble in the presence of sodium fluoride? All right, and this is a concentration, so we'll put units of molarity there. Right, our initial assumption was that the presence of this should decrease the solubility, right? Which means, are we dissolving more or less into solution? Less, right? If we make it less soluble, less should be dissolving, right? So this x value, when we compare it with our pure water, should be less. And so this was pure water, it's 10 to the minus 4, and this was for the presence, 10 to the minus 8. So did that follow what we expected? Right, is this less than 10 to the minus 4? 10 to the minus 8 is a lot smaller than 10 to the minus 4, right? So it's about 10,000 times less soluble in the presence of sodium fluoride, right? So this followed what we expected, right? So we knew that this value should be less than in the presence of pure water. Why? Because the common ion effect and Le Chatelier's principle indicated that to us, and we can show it explicitly here that the molar solubility is actually less. All right, so the trick here for this problem is you set up an ice table for each of these. You solve for the molar solubility, which is just this change here, because that's equal to how much of your solid actually goes into solution, right? That's how you know that that's the molar solubility. And then you compare that with the common ion, right? Where now you have a little bit of concentration initially of one of your ions here. You use that to then set up your equilibrium equation here again for the equilibrium constant. We can use the small x approximation to simplify this polynomial. And then we solve for x again to get the new molar solubility, right? So we can explicitly calculate which solution it's going to be more soluble in. All right, so let's take, that was a bit of a long problem, so let's take like a 15-minute break. We'll be back at about 10, and then we'll finish up this lecture on solubility equilibrium. And if you have any questions, you can come. It was a period, like a bullet point right here. This is a bullet point. And BC is just because. Oh, yeah. Questions on that problem? All right, I know you guys had 15 minutes to think about it or so. Is there anything you guys want me to clarify? Where the small x approximation comes from? How we used the concentration of sodium fluoride to get our equilibrium concentrations, or anything of that nature? No? Okay. All right, well, if you do, I'm sure we will all have questions about it. Reach out. Go to Destinos and do whatever you need to do. All right, so the same way a common ion can affect the solubility of a compound, the pH can as well, right? And so the pH, does anyone remember what pH is related to? The concentration of what two ions? We'll talk a lot about this, just when you guys are sick of pH, and acids and bases.
Hydrogen and one more.
Yep, it's hydronium, which is an extra protonated water, H3O plus. Let me do that nicer. H3O plus, or OH minus, or hydroxide concentration. So pH can be expressed in terms of both of these concentrations here, right? So the presence of these ions in solution is what makes it acidic or basic, and we'll talk a lot about that. And so if we look at this reaction here, right, this is going to be a metal hydroxide compound, right, because OH minus is called hydroxide, and it's coordinated. This is a solid, right, so if you actually get your base, a lot of times you dissolve some sort of hydroxide in solution, and it changes the concentration of OH minus in this case, right, because it adds that. Dissolves, this is the dissolution reaction we were just talking about now. So if we change the pH of the solution, let's say we increase the OH minus concentration, what should happen to this reaction?
It'll go towards it.
Right, if we increase the concentration of this,
Oh, increase, then it goes.
yep, then it's gonna move the reaction in the left direction, right? And an increase in hydroxide concentration correlates with an increase in the pH of the solution, right? So we'll just mention this right here, an increase in OH minus equals an increase in the pH, a decrease in OH minus is a decrease in the pH, and then we also have the H3O plus equivalent. An increase in the H3O plus concentration is equal to a decrease in the pH, and a decrease in the H3O plus or hydronium concentration is an increase in the pH. Right? H3O plus is usually what we use to determine how acidic a solution is. So as this goes up, the pH gets lower because it becomes more acidic. Right? pH 1 solution. So if we're increasing OH minus, that's like increase in the pH. So an increase in the pH will make this less soluble. So this would have to be a acid soluble metal of hydroxide. Right? So all this is doing is just applying the common ion effect, right? Applying the common ion effect and Le Chatelier's principle to H3O plus and OH minus. Right, so really nothing's changed here. All that we're doing is we're changing the nomenclature a little bit, right? And these changes in pH just correspond to changes in these two concentrations. Right, and so you can look at it one of two ways, and when we do acids and bases, you'll find you can do everything in terms of acids or bases, right? A decrease in pH is either an increase in H3O plus or a decrease in OH minus, right? So you can change the pH both ways. You can come up with a common complex ion that decreases this concentration, and that's the same thing as decreasing the pH as well. Right, so if the pH is high, the high concentration of OH minus, or you could say the low concentration of H3O plus shifts the reaction to the left. And that's exactly what the first example that we showed on the previous page, right? If we increase OH minus, that'll shift the reaction to the left. If the pH is low, then the OH minus concentration, the H3O plus concentration, trying to stay color coordinated. The H3O plus concentration is high. And so as the magnesium hydroxide dissolves, the H3O plus reacts with the newly formed OH minus, driving the reaction to the left, right? But the high H3O plus concentration is equivalent to a low OH minus concentration, right? So that's like the same thing as decreasing OH and shifting it to the right. This extra sentence here, all this is saying is that basically as this is added to solution, right, these OH minus ions are reacting with the H3O plus that's already in solution. And what happens when H3O plus and OH minus react to each other? Does anyone know? Right, what do we get if we have, right, we have this secondary reaction that's happening, right, OH minus plus,
Water, right?
yep, that's exactly right. This reaction will just form liquid water, right? If you take acid and base and mix them together, they just form water, right? That's how you neutralize an acid and base usually. It's a very exothermic reaction, so it'll get very hot, but that's what happens. So what this is saying is as you add this to solution, you create OH minus. That OH minus immediately reacts with H3O plus because it's a very acidic solution and makes water. right? So what is this reaction doing as soon as this reaction happens, right? It's effectively taking away this ion, right? So this is a separate reaction that's taking away this ion, that's forcing this reaction to move right. Which means that, let's say you have this solid in a precipitate in your solution, you add acid to the solution, all of a sudden that added acid starts reacting with all of this. The dissolution reaction or the dissolving process now has this concentration being decreased. Le Chatelier's principle says now that you're moving this reaction to the right. So I know before I was talking about, well, if you're reducing the concentration of a reactant or a product, it's like a sink is under that reactant or product, and the reaction flows in the direction to increase that concentration of whatever's being reduced. Here, it's not, it's not a sink, right? We actually have a reaction that's happening. This reaction is taking the OH minus from here and forcing it into something else, because this is a very favorable reaction. This reaction is like, always going to happen. So it's taking the concentration of OH minus away, forcing this reaction to happen. When this reaction is forced to happen, now you're forcing something that was insoluble to be soluble in solution now. Right, so this is taking advantage of the fact of the common ion effect to then increase the solubility of something, right? So here we've decreased the solubility of MgOH2, and here we've increased the solubility of MgOH2. Right, and again, in red here, I just have this because you can think of it in two ways. With pH, you can always think about it in terms of OH concentration and H3O plus concentration. And they're both equivalent, they're just inverted from each other. And so here we have another example, right? So we have calcium oxalate, right? So this is our dissolution reaction. And we want to determine the effect of lowering the pH. Well, the oxalate ion is a conjugate base, right, of a weak acid, so it means it's a very basic compound. And if there's H3O present in solution, so we add acid, right, we're adding acid to the solution, it'll cause the protonation to form oxalic acid. All right, so we form oxalic acid, right, the conjugate base, or this would be the conjugate acid of the oxalate ion, and because we've increased this and forced this reaction to happen, we've effectively done what to the concentration of the oxalate ion? And this is the oxalate ion.
Lowered it.
We've lowered it, right? So this effectively lowers the concentration of C2O4 2 minus, right? So this is the net effect, right? The presence of acid now causes the conjugate, or the oxalate ion, to react with a hydronium ion in solution, which decreases the concentration of this, which shifts the reaction to the right. And how far into precipitation did I go? And so we can use this to determine when things start to precipitate, right? So precipitation occurs when ions of a semi-soluble salt come in contact with another, right? And so I just mean semi-soluble because not all of it is going to dissolve, so it's not a strong electrolyte. It just means it'll partially dissolve, right? So it partially dissolves, or it has a small KSP. So we can ask the question, what concentration of ions will cause a substance to precipitate? Right, and we can use the ideas of equilibrium, our molar solubility, to then answer this question. And so we can, the same way we use the reaction quotient to determine the common ion effect on solubility, we can do the same thing for if we have two semi-soluble salts come in contact with one another, which one will precipitate and which one won't. So we can use the reaction quotient, except in this case it'll be QSP that we're looking at, right? So these are the initial concentrations. And so if we had the QSP for this reaction here, the calcium fluoride reaction that we already looked at, this would just be the concentration of 2 plus and F minus squared, right? It's our usual reaction quotient, except these are the non-equilibrium concentrations. And again, we use this because we compare it to our equilibrium constant to determine which way the reaction will go. And so when we're determining which way the reaction will go in dissolving something, we're saying, is it going to be aqueous or is it going to be solid? Which means, is it going to dissolve or is it going to precipitate, is the question that we're asking when we're looking at QSP here. And so we can interpret QSP the same way we did before, right? It's the same thing, except now, our reactants and products, right? We don't really have anything on the reactant side because it's a solid for all of these cases. We're just looking at the relative magnitude, and it tells us how much products do we have right now versus how much products do we have at equilibrium, right? So if we have QSP is less than KSP, the solution is unsaturated, right? If we think about what this means, so I'll use red for QSP, F minus 2, and we compare that to Ca2 plus, F minus squared. This is KSP in QSP, right? If this value is less than this value, it means that our concentrations for these at equilibrium are higher than what they are initially, which means that we have to make more of these aqueous products, right? We have to make more of the aqueous products, which means the solution is not saturated. We're going to continue to dissolve this solution we're going to continue to dissolve this solid into the solution, right? Because this reaction, again, was in kind of room CaF2, solid, Ca2 plus, aqueous plus 2F minus aqueous, right? If these concentrations are too low, we need to make more of them to reach equilibrium, right? So this reaction is going to move in this direction. What's that mean? We're going from solid to aqueous, right? So the reaction moves forward. If they're equal to each other, we know the solution is saturated. That just means that we're already at equilibrium. Any additional solid will not dissolve, and then removing any solid or any of the reactants will cause more dissolution. And then if the solution, if we have QSP larger than KSP, that means the concentrations are larger than what they should be at equilibrium, which means we need to get rid of some of them to reach equilibrium. So that means that the solution has too much of the ions dissolved in there, and then you're going to form precipitate, right? You're going to cause it to crash out of solution, right? This is if you, right? So if we think about temperature, right? Temperature makes things more or less soluble. When you think about cold or warm coffee. is sugar more or less soluble in cold or warm coffee?
Or wait,
More soluble, right? Because if you have warm coffee and you put sugar in it, it's going to dissolve, whereas iced coffee, it'll sit at the bottom, right? So if you take coffee that has a certain amount of sugar in it, and it's iced coffee, and there's a bunch of crystal sugar at the bottom, and you heat it up, that salt will start to dissolve in solution. You then cool it very rapidly, and the solution cools, and now you have a super saturated solution. What happens is the equilibrium now needs to change, it needs to shift back, so it's going to shift more, make more of the solid. So your sugar is going to crash out of the solution. All right, so the same idea here, we're just putting a kind of quantitative way to measure that by looking at QSP and KSP. All right, so here we have an example. We have a solution containing lead nitrate, and it's mixed with one containing sodium bromide. After mixing, the concentration of lead nitrate is 0.150, and that of sodium bromide is 0.0035. Will a precipitate form in this mixture? Right, so the KSP for lead bromide, right, this is for PbBr2 is equal to this value right there. And so we're going to be determining if it's precipitating or not because we're given the concentration of lead nitrate and sodium bromide at equilibrium. And we need to ask, is this going to precipitate or not in this solution? And so the first thing we need to do is write the dissolution reactions for everything here. So we have lead nitrate, NO3, is a solid. And then that creates lead 2 plus, 2 nitrate ions, minus. We have sodium bromide, which is going to be a strong electrolyte. So that'll give you exactly the concentration of Na2 plus, not 2 plus, 1 plus, plus bromine ions. Both of those are aqueous. And then we have our actual reaction that we're given KSP for, which is going to be our precipitate, or what we're looking at to see if it's going to precipitate in solution. All right, so this is going to be PbBr2 goes to lead 2 plus 2Br minus. And so how do you think you're going to determine if this solution will form a precipitate, a lead bromide precipitate? Like, how are we going to use the values that are given here, right? We're given some concentration values. And then asked if a precipitate will form. What do you guys think? How are we going to determine quantitatively if a precipitate will form or not? We need to find QSP, right? We need to find QSP, and then we compare that with KSP, right? And so what is QSP equal to in this situation?
Would be Pb plus 2Br.
Yep, it would be the concentration of PB 2 plus, and then BR minus squared. Right, where do we get these concentration values from?
From the KSP.
Well, we're going to compare this value to the KSP, right? So the KSP is equal to the equilibrium concentration.
Yes, yeah, but like that PBR thing, like,
The-
that's what we compare it to, right?
Yeah, we're comparing it to this KSP for this PBR.
Yeah.
Both these concentrations, which are initial concentrations, are the concentrations of each of these electrolytes or salts, semi-soluble salts that are mixed together in solution. So this should be, these are each going to be the concentrations of the semi-soluble salts in solution. And so this is equal to the concentration of lead comes from our lead nitrate, which is 0.0150 times the concentration of our sodium bromide squared, and then we can plug in these values, and that gives us 1.84 times 10 to the minus 7. All right, so now we compare this value and this value to each other. To then determine, go ahead.
It won't precipitate.
Yeah, it shouldn't precipitate, right? Because this value is less than the equilibrium concentration, right? Which means that we're still going to be going forward in this reaction, right? This KSP is this reaction going forward. Which means that if we have these concentrations, we get a QSP that's less, meaning these concentrations are less than what they need to be at equilibrium, which means we're going to be keeping things in the aqueous phase here. So this is less than, which means that no precipitate, which is usually abbreviated PPT, forms in the solution. Alright, so each of these semi-soluble salts give us the concentration of our two ions that form the precipitate, right? So this is our precipitation reaction, our dissolution reaction. In comparing those, we just, the same idea with anything in equilibrium, we just see which way does that imply that the reaction shifts, towards the reactants or the products. Shifting towards the reactants just means we're shifting towards the solid, so precipitate will form. Shifting towards the products means that we stay dissolved, right? Because we're shifting towards the aqueous stuff. All right, any questions on that? All right, what about if we ask, well, what is the minimum concentration of sodium bromide that will precipitate lead bromide? Are these the same salts? Yeah, still the same salts. Right? How do you think that we'll approach this, right? What is the minimum concentration? Where do you think the crossover is from precipitating to dissolving? At what point is that crossover exist?
When they equal each other.
When they equal each other, when QSP and KSP equal each other, right? So this is saying given the same amount of lead nitrate, right? So what's implied when this is asked is that we're given the same amount of lead nitrate, and that gives us the concentration of Pb2 plus. Right, that's where we got the concentration of Pb2 plus, was the amount of lead nitrate that was in solution. This is the same as the previous part of the question. And we know the crossover from precipitation to dissolving happens at equilibrium when QSP is equal to KSP, right? So what we're saying, really, what this question is asking in different ways, well, what's the concentration of bromine gonna be given this concentration of lead at equilibrium, right? As another way of phrasing this question. And we have our KSP at equilibrium, right? So this is at equilibrium, is equal to Pb2 plus, and then Br minus squared. So what do we have here and what do we need to solve for?
We have KSP and do we still have PV from the other?
We have, yeah, exactly. We still have the concentration of lead too, because we're given that in the first part of the question, right? So we're given both of these. And since we're given both of those, that just means we have to solve for whatever the bromine concentration is. And the bromine concentration, the last realization is that the bromine concentration equals the concentration of sodium bromide. So we can solve for the bromine concentration. We get KSP. I'll go back in a second. You guys finish writing 2 plus Br minus squared, divide both sides. Pb2 plus, Pb2 plus. This cancels out on this side. Br minus squared over KSP, Pb2 plus. We can now square root both sides or raise both sides to the 1/2 power. And we get the bromine concentration is equal to KSP over Pb2 plus to the 1/2. Right, and when we plug this in, this will give us the concentration of sodium bromide that we need to actually precipitate this out into solution. And so, without plugging that into my calculator, this should be about 0.0176 molar. It's saying for this given amount of lead nitrate, which gives us the concentration of lead ions, and given the equilibrium constant of this precipitate forming or dissolving, what's the concentration of the other salt we need to then get the precipitate to form, right? And this is the point at which if we start adding more sodium bromide, or if we start adding more sodium bromide, I'll go back in a second. We start adding more sodium bromide, right? We start adding more of this. Which direction is this reaction going to shift? Left or right? If we're increasing this, it should shift left, right? Towards the solid. So at this point that we just calculated, anything after that is going to go straight into the solid state, right? Because we've pushed out of the equilibrium, we have to make more solid lead two bromide to actually get the equilibrium to stay the same. All right, so this is, I'll pause on this for a second in case some people were still writing here. And so again, I know it seems like a lot of these ideas are different from each other, with the gas phase reactions, aqueous reactions, and now with solubility, but it's all really the same idea. We're just looking at which direction this reaction shifts. The only difference here is that this reaction now represents something precipitating in reaction. Why? Because one of the reactants is solid. Whereas before, we're just looking at maybe what's the new pressure of two gas phase reactants after they've been put in a chamber. Right? So this equilibrium constant still represents the same thing, it's just the chemical reaction itself is slightly different. And we can use these ideas in equilibrium to then interpret what should happen for these other chemical systems as well. All right, then I'll leave it right here.